Well, we can at least get started with a slow rolling introduction. So we're really happy to be here today to hear the thesis. We don't call it a thesis defense. We can have really hard questions, but a thesis presentation by Medhini. And it's been wonderful supervising Medhini. She came in already very experienced in the area that she ended up focusing on and dominating. I think multimodal image and video, and especially long-term video understanding, has been a problem that's just been of increasing interest and importance as large-scale models are more and more prevalent. So when she started, I feel like these areas maybe were considered somewhat niche or not necessarily in the mainstream, but now they're clearly in the mainstream and not only important to understanding video just for the sake of understanding video, but as the earlier question foreshadowed, with many applications, including in robotics and healthcare and other places as well. So with that, I'm very happy to be introducing Medhini and looking forward to seeing her final presentation.
Thanks so much for the introduction, Trevor. Yeah, I guess I'll get started. Yeah, thanks everyone for joining in person and on Zoom. Thank you so much. Really excited to present my work on multimodal long-term video understanding. Before I begin, major thanks to my committee, mainly Trevor, my advisor for the past 4 years, and the rest of my committee, Alyosha, Rose, Jitendra Malik, and Cornelia Schmidt. Yeah, thanks so much. So I'm going to begin. Oops. Yeah, so my work is mainly on videos, but I guess the biggest question is, why should we learn from videos? Why not just images? Mainly because videos are everywhere, and there are thousands of videos which are being uploaded on the internet every second, and we need large video models which can understand all of this content. Videos are also a rich source of information. So if you look at the slide, just this image, you see that there's like a person in the kitchen and you can tell that they're cooking. But now when I play the video, now this gives you so much more information. You can see how the objects interact with one another. You can also understand the temporal dynamics of the scene a lot better. And you can see that they're moving around, not making popcorn. But videos are also multimodal. Now see if I play the same video, but with audio.
Put that at the bottom. Very important, get your pot holders, spread the oil on the bottom, have your lid of your pan ready in your other hand, and go ahead. You hear that? It's starting to pop right now.
So now that I played the video with audio, you could understand the sound of the objects interacting. You can understand like how what sound each object makes, and also the speech of the person sort of draws our attention to what they're doing. And so all this rich information can now be learned from videos. Videos are multimodal. They contain speech, which can be transcribed as text. They contain visual information. They have audio, and another important modality, which is time. And it's the ordering of events in a video. Moreover, all of these modalities in videos are correlated with one another. So you can see that the speech can be derived from the audio, and it corresponds to the audio. The visuals also relate over time, and so on. So what can we do? Which means now we can predict one modality from the other. So given the video and the audio, we can extract the subtitles or the speech from it. We can also predict the ordering of frames in a video and predict future frames given the past frames and such. So all of this allows us to learn video representations in a self-supervised manner. But of course, I'm not the first to think about this. There are several people who have done this in the past. So works like VideoBird, Merlot Reserve have done exactly this, predict one modality from the other, and train large models which can learn representations. So what is missing? Mainly understanding really long videos. You can see video models are mainly focused on short video clips, which are less than 2 minutes long. So here are some of the data sets that most of the video models work on. So there's kinetics, which is 10-second long videos. There's how to 100M, which is a minute or two long. long, and Epic Kitchen's less than a minute long. And all of these videos are pretty short, but if we want to understand really long videos, we need to train on data sets which are longer. And so understanding long videos and extracting semantics and structure from them is still an open problem. So this is what I hope to target during my PhD. My work was mainly focused on understanding long videos using multiple modalities. I'm going to provide a brief overview of my works and then deep dive into 4 of them. So in the first work, we try to synthesize really long videos conditioned on an audio signal. So imagine a video of a person playing a guitar to a particular song. And say you have a new song and you want to synthesize a new video which matches this song. So let's look at the first one. It's okay. I think it's some less. Thank you. So that was the video of a person playing a song, and now I'm going to play a second audio clip, which is a different song from the one you heard. So the idea of this work was to try and synthesize a new clip, which would borrow the frames from this first video, but match the conditioning audio be the second one. And so this is what our method synthesizes. So this allowed us to generate new videos which are much longer than the first one and also condition it on a new modality, which is audio. In the second work, after having focused on synthesizing long videos from short clips, I tried to do the reverse. So try to go from a really long video and generate something which is shorter and summarizing new videos. So in this work, we tried to use language as a query or a conditioning factor to focus on relevant scenes in an input video and synthesize a short clip. Next, having looked at generic videos, my next work was focusing on one domain of videos, which is just instructional videos. So how can we summarize videos, but now instead of just any general video, can we just focus on instructional videos because they contain more structure? So in this work, we again try to leverage cross-modal cues like audio and language and visuals and try to synthesize something which is smaller and a concise version of the input video. Having seen instructional videos, one thing that was missing at this point was that there's no good way to represent steps in an instructional video. And so we were trying to summarize these videos and make them shorter, but still we wanted to learn a better way to represent the steps that you see in the video. So in this work, we focused on learning task structure from the same videos and trying to find a better way to learn representations for the steps that you see in instructional videos. And this is a more recent work. It diverges a bit from videos, but it's still about learning steps from multiple modalities. So in this work, we try to leverage large language models to look at either an image or a group of images and answer questions about them. Again, by looking at both the modalities, both visual and text information of the question and captions related to the image. So I'll be talking about some of these in a bit more detail, starting with the work on video summarization. So this is joint work with Anya and Tor and is presented in Europe. So in this work, as I mentioned, the goal is to go from a really long video and make it something shorter. And so that's what we call a summary, but let's see what a summary is. So here's a video. It's a 1 minute, 30 second long video. And for most of this video, there's nothing that's happening in it. Yeah, and here's a summary which is synthesized by our method. So you can see that the summary essentially just highlights the important scenes in that 1 minute, 30 second long video. And you get the shorter clip, which is only 12 seconds long and picks out all of the events that are happening. So it's only the relevant scenes where the people are jumping into the water or swimming out of it. So summary is a good abridged version of a video, which still conveys all of the whole story and features the important scenes. But the importance of a scene can be very subjective. So if you take this video of a national park tour, now this video is 2 hours long and it features so many different scenes. It contains like animals, restaurants and shopping centers, water bodies and such. So which of these scenes are important and which should belong in the summary? What we notice is that language, like captions or user-defined queries, can serve as an effective prior for visual saliency. And most of the prior works had failed to exploit this. They didn't use any form of language in generating summaries. So that's what we did in our work. We introduced a language-guided multimodal transformer for both query-focused and generic video summarization. So in the query-focused setting, given that same video of the national park tour, we allow users to specify queries, like say, give me all the scenes containing restaurants and shopping centers, or all the water bodies such as lakes, rivers, and waterfalls. Now, our method, Clipit, can take that same video and generate something shorter, and here are some frames on what it generates. It just contains scenes which are pertaining to the user-defined query in both the cases. So using our method, viewers can now customize summaries by using a natural language query. But what do we do if there's no user-defined query? In such a case, we can still use language in the form of a caption. So we take that original video of the park and pass it through an automated captioning system to generate a caption of the video. It would give you something like, this is a video of a park. It contains waterfalls, geysers, and such, and restaurants and grocery stores. And so now the method learns to pick out all the scenes which are corresponding to this caption and highlights only those scenes and gets rid of a lot of irrelevant content. And so yeah, this way we were able to use language to summarize videos. And I'll go a bit more into the method. So given the video, we first extract frames from it. Next, if a user-defined query is present, we use the query, or otherwise we use a caption generator to generate a caption. We use pre-trained clip model to extract clip text embeddings for the caption and the query, and clip image embeddings for each of the frames in the video. Next, we use a language-guided attention head, which learns to fuse information and across both these modalities and contextualize them. So now we have these attended features for each of the frames in the video. Our goal is to now assign some sort of scores to all of the attended features, which would tell us which of these frames should belong in the summary and which we should discard. To do this, we use another transformer, which looks at all of the frames at once, and then can assign a relative importance score to each of the frames in the video. So using this, we have some scores for every frame in the video, and our goal is to now try and see how we can select which should belong in the summary. But how do we train this? So it turns out video summarization comes with a lot of benchmark data sets where someone has manually annotated every frame in the video with an importance score. That's cumbersome, but it's great that we have that. So we can use that supervised data set to train our network. So the scores that were manually annotated by annotators can be used as a ground truth supervision, and we can train our network using classification laws. But of course, this is not always provided. And so what do we do in the absence of the supervision? We can use an unsupervised method. So we'll introduce two losses, diversity and reconstruction losses. So the three losses that we use in our work, first was just the classification loss. It's a simple binary cross entropy loss for classifying which frame should belong in the summary and which shouldn't. Second is the diversity loss. This basically ensures that all of the frames which are selected to be a part of the summary should be different from one another. And it reduces any redundancies in the summary. In the reconstruction loss, we ensure that the reconstructed summary should be very similar to the original video. So it should contain everything that's important in the video. And this acts as like a regularization term by making sure that the embeddings for the two are similar. So we can train our network in two different settings this way. In the supervised setting, we combine all three losses. And then in the unsupervised setting, we just use the diversity and reconstruction losses. And that's how we trained Clipit. And for inference, we still want to select some frames and synthesize a video. Typically, how video summaries work is that you assign the summary to be a percentage of the input video. So you're going to say that this user wants a 15% length duration of the input video, or like a 30-second summary of any video that they see. So our goal becomes now to fit some percentage of that input video into these 30 seconds. And we have scores for frames. So what we do is convert the frame scores to short scores. So you don't want to just have like frames which are different from one another, then your result will look pretty jarring. So what you want to do is divide the video into smooth shots, and then convert the frame scores to scores for each of these shots. Now that we have short scores and we have like a budgeted time limit, we use Knapsack to figure out how many of these shots should belong in the summary and which of the highest scoring shots should belong in the summary. So this way we can construct like a new video which just stitches together all of these important high scoring shots and constructs this video summary. So let's look at some examples. So first, maybe the quantitative results. So we were able to achieve state of the art on both generic and the query focused video summarization benchmarks, and in both of the settings. So some of the benchmarks that I mentioned are SumMe and TVSum for video summarization. So typically what people report is the F score. It measures the overlap between your ground truth summary and your generated video summary. And you evaluate this in 3 different settings. So in the standard, augment, and transfer settings. In the standard setting, you're training on the train set from SumMe and evaluating on the test set from the same data set. In the augment setting, you train on all of your trained data sets, so like SumMe and TVSum, and then evaluate on just SumMe. And in the transfer setting, you train on the other data sets, so you train on TVSum and evaluate on SumMe and vice versa. So the transfer setting is the most challenging one. It's testing the model's generalization capabilities. And we see that we're able to achieve like a higher improvement specifically in this setting. That was the supervised case where we used all 3 losses. And now in the unsupervised setting where we use only diversity and reconstruction losses, we observe similar performance gains on all the 3 settings. We also evaluated on the query focused benchmark. So this is where a user query is provided and we're not generating any captions, we're just using the user defined query. Here we see a much higher improvement compared to the previous baselines. They used just graphical methods, whereas ours was a transformer based method. And so this led to stronger improvement of about 10 points. And these data sets are about like 2-hour long videos. So it's much longer than the previous data sets as well. And here are some qualitative results. So in this is a video from the TVSum data set. It contains an input video of a person making some sort of a sandwich. The ground truth summary essentially picks out all of the frames in the video which correspond to key steps in the process. So whether assembling the sandwich or making the batter and such. So first we tried not using any language guidance. So this is just a clip image embeddings passed through a frame scoring transformer. So here we see that it does pretty well. It can pick some of the important steps, but it also includes other irrelevant information like the person eating the sandwich or the person talking to the camera and such. And then there's our method, Clipit, where we include the language guidance or the caption. So here you see that the caption already highlights pretty much what is important to the input video. So it's already a very good summary. So it talks about important actions like cutting the food, mixing the food in the pot, and such. And so now our method is able to clearly pick out only the scenes which correspond to these particular actions or events in the video and gets rid of irrelevant information, like the person talking to the camera. So some takeaways from this work are that we can now summarize videos by using language guidance, either in the form of user-defined queries or captions. And we were able to achieve strong improvements on both generic and query-focused benchmarks using this technique. And users can customize their queries using natural language. However, there are still some issues with video summarization. The first is that most of these data sets that I mentioned, SumMe and TVSum, they still require manual annotations. So someone needs to go through every frame and assign an important score, and that's the only way you can evaluate how well your summary is doing. And this is cumbersome. So which means that all of these data sets are quite small and sometimes subjective. So TVSum is about 25 videos, SumMe is 50 videos. So yeah, this is really small to evaluate your method on. So what we thought about is like, is there a single solution to both these problems and can we fix these 2 issues? Turns out, yes, there is. If we focus on only one domain of videos, say instructional videos, we can solve both of these problems. So that's what we did in our next work, summarizing instructional videos. So in this work, we used instructional videos along with the speech and text information and use all of these cues jointly to construct summaries. This is joint work with folks from Google and was presented at ECCB. So why look at instructional videos? So mainly because there's abundant instructional videos which are available on the internet. There's like thousands of videos for any task that you can think of on YouTube. Also in instructional videos, you have the speech, which can be converted to subtitles. And now the subtitles provide natural supervision. And this is missing in any other generic video where you will have to rely on captions. Also, the videos in general are procedural and they contain structure. So someone's trying to perform a task, there's steps, and these steps are occurring in a sequence. And so all of this is useful and allows us to maybe clearly define what is a good summary. And perhaps in this case, there's no need for manual annotations like in the generic video setting. But what is a good instructional summary? So if you search YouTube for a video on how to make coffee, you're going to get something like this. And this is now like 2 minutes, 30 seconds long.
Hey, American coffee lover, taking a break with a rich, robust, flavorful, and aromatic cup of joe? No? Well, how come? Hey now, don't do anything rash.
So this really long video already contains like 10 seconds of irrelevant content where the person's just not talking about anything useful to your task. And so what you want maybe is a summary that's something like this. It just is 30 seconds long and it picks out all of the important steps in the video and just highlights what needs to be done. So we can already clearly tell what is a good instructional summary. It's just one that you can perform the task by watching the summary and it highlights all of the important steps. But which steps in the video are relevant to a task? And this is a question we still had to answer. So we looked at a lot of instructional videos for several different tasks, like making a pancake and such. And what we saw was that if a step is important to a task, it's going to appear across multiple videos of the same task. So imagine making a pancake. Any video that you see on YouTube for making a pancake is going to have a step where someone's whisking the eggs. And you know that now this step is pretty crucial to the task. Again, if a step is important to a task, the person who's demonstrating this particular task is going to speak about it. So they're going to say, and now I'm going to melt butter on a pan, or now I'm going to add salt to something. And so you know that this is a crucial step. So we mainly relied on these two objectives to create a large data set of about 12,000 pseudo summaries from 12,000 different videos. And now we use these 12,000 summaries to train our network. So our instructional video summarization pipeline mainly consists of two different stages. So the first one is where we generate pseudo summaries using weak supervision. All that we need is just the task label, like make strawberry cake, grow lemon tree and such, and multiple videos of the specific task. Then we rely on the two objectives that I mentioned earlier to create summaries for each of these videos. Now that we have the videos and the corresponding summaries, we train a network to do this automatically. The reason being, at inference, you don't want to, again, rely on fetching other videos of the same task and such. And so you just want to be able to give your video to a network and have it generate a summary. And so this network is, again, trained with all of these pseudo summaries that we generated. So I'll talk about both of these steps in more detail. So first, generating pseudo summaries. For this, we divide the video into non-overlapping video segments and extract features for each of these segments using a pre-trained video model. Next, we cluster the segments together along the time axis, such that two segments are grouped together if they are both adjacent in time and also similar to one another. So it's like a moving window that's moving across the video, and you're grouping the segments together if they're similar to one another. When we do this, we notice that the resulting clusters correspond to the steps in the input video. So roughly, we have now taken the video and divided it into steps in the video. And what we need to do next is figure out which of these steps are important and which of them should belong to the summary. So to do this, again, we go back to like the two objectives that I mentioned earlier. First is task relevance. So is the step relevant to the task? To determine this, we take the embedding for the step, compare it to the embeddings of all other steps across all the videos of the same task, and give it a similarity score based on this similarity of embeddings. So you have one task relevance score, Next, we compare the embedding to the subtitles in the video. So just the transcript, and we get the text embeddings for that, compare it with the video embeddings for this particular step, and assign the score based on the similarity to the subtitles. So we call this a cross-modal saliency score. So then we average both the scores to obtain a single score for each of the steps in the video. So now that we have the scores, we just have to threshold the highest scoring steps and stitch them together to construct the pseudo summary. So what this whole process gave us is we have videos, and we've now constructed like summaries using no supervision, just like these two objectives of task relevance and cross-modal saliency. And we obtain scores for each of the frames in the video. This is great, which with this now we can train a network. This process is of course noisy, but the hope is that this network will learn about the noise and learn to summarize videos despite any errors in that unsupervised process. So this is our video summarizing network, very similar to Clipit, where we just take the video, divide it into video segments now instead of frames, and also take the subtitles as input. So we're no longer using captions like in Clipit. It's been replaced by subtitles, and we have video segments instead of frames. So we embed each of these using video models or a pre-trained language model, and extract and then pass them through a segment scoring transformer. Again, this transformer learns to contextualize information from one modality and across the whole video, and assign scores to each of the segments. Since we have the scores from the previous step, we can just train this using the scores from the pseudo summaries. And then we just pick the highest scoring segments and stitch those together to be a part of the summary. So that was just the training, and we still need a way to evaluate our method. So as I mentioned earlier, the prior works relied on manual annotations. So most of the data sets were still expensive to collect and highly subjective. And now we've been able to train on 12,000 videos, and we need something which is comparable, like a large test set to evaluate on. And the test sets of prior works are pretty small. They only contain 10 to 20 videos because someone had to manually annotate them. So ideally, we wanted something which is clean, automatically sourced, and also scalable. And we lucked out and found just this. So we looked at WikiHow videos. It's a great repo for instructional videos. It contains like videos for several different tasks, like how to make a veggie burger and such. So now this video is about 2 minutes long, but what it comes with is also like this nice annotated page of like all of the steps in the video. So someone's manually picked out all of the steps and the images or clips corresponding to those steps from the video and annotated this, which is great. So now we can take all of these clips and shorter clips and stitch them together to make a summary. So we created this evaluation data set, WikiHow summaries data set. So it contains instructional videos for about 2,000 tasks. And each of these videos come with steps, like images and short clips, which also illustrate the step. Next, we localize the steps in the videos and stitch those localized clips together in order to create the video summary. And this method also allows us to obtain important scores for every frame in the video, since we're localizing the clips in the video, and if it was present in the clip, then you know that this is part of the summary, and so it should receive a score of 1, otherwise you ignore that frame. And so this way we can obtain scores for all of the frames without any manual annotation. So this was created completely automatically and was only manually verified by us. And so now we have this method which we've trained on like 12,000 videos and evaluated on 2,000 or more videos. And yeah, what we notice is that like main biggest improvements are on top of these smaller models which were trained on like just 50 videos and such. So here is a comparison. So this is our method IVSum, which is compared to our prior work Clipit. Here the task is making an origami paper claw, and the step labels that you see here are just the ground truth steps shown for reference. So yeah, each of the steps are not used as input or anything, just for reference. So what our method does is it's able to pick out frames corresponding to all of the steps and creates a summary where it focuses on all the steps in the video. So we measured step coverage, and we noticed that compared to the baseline, method achieves a high step coverage each time. The baseline, however, misses out some of the steps, like fold into triangle and such, and also it picks some irrelevant frames corresponding to some of the steps, like make valley, fold, and tuck dip into picket. And our method is able to pick more relevant frames, mainly because of the fact that it was trained to see multiple videos of the same task, and also it uses language guidance from the subtitles. So some takeaways of this work. We introduced a weekly supervised method for summarizing instructional videos. And we're able to train and test on lots of data as opposed to the 50 videos in the prior work. We also see that cross-modal saliency and task relevance are both useful cues for finding out which steps in the video are relevant. And training on a lot of pseudo summaries was a lot better than using a small clean data set, as we noticed. But instructional videos contain all of these cross-modal cues, and there's a similarity between a lot of videos of the same task, and there's this common structure across all of them. So the next question was, can we learn something else from a lot of instructional videos? So this is what we did in the next work, learning task structure from instructional videos. So we're trying to learn if we can perform a particular task or understand the sequence and ordering of steps in a task by watching several different instructional videos. Also, I should have mentioned, if someone has questions on Zoom, please unmute yourself to ask questions. Okay, so the question we had for this project was, how do we learn representations for steps? So you can learn a step representation from a single clip. So you can take a step, like say melting butter in a pan, take many different clips which are performing this particular step, train a network which assigns this label, and learn a representation this way. But however, most of these steps don't occur independently. But most of these steps in a task are related. So melt butter in a pan is typically a part of a much bigger task, where you're dripping bread in batter, frying bread in the pan, and then making French toast. And all of these steps are related. So we argue that if you want to learn good step representations, these representations should be context aware of the task that they're a part of. And so in order to learn task structure, we need to be able to learn step representations jointly and not independently. So that's what we did in this work. We learned to represent steps by masking them. So given a video, we pick out all of the steps in the video and pass these as input to the network, and by randomly masking out about 50% of the steps in the video. Then we train a transformer network, which essentially is a hierarchical transformer, which takes all of these video steps and learns to assign the labels for each of the masked out steps from the context of the surrounding steps. So we trained this network on all of how to 100M. So we used 100 million video clips. The how to 100M dataset comes with the videos and the associated subtitles. What we needed was the labels for each of these videos. So to obtain labels, we used WikiHow. It contains the tasks and all of the associated steps for this particular task, for several different tasks, and all of the tasks that you can find on how to 100M. So we use WikiHow as a weak supervision and localized each of the steps that you find in this task back in the original subtitles. So this way, what we got was a mapping between the video clips which occur in how to 100M and the step labels that you would find on WikiHow. So this gives us fair data that we can train the network with. And essentially, we can just train it using a supervised classification loss and predict the labels for the master steps. So this is the pre-training of our network. Basically, we take the video, mask out some steps, and train this intermediate transformer model, which learns to predict what the master steps are. And this is just trained using classification laws. Our goal was to try and see how well these learned representations would perform when you evaluated on task structure capable downstream tasks. So essentially, does this capture what is happening in the task? Are these steps aware of other steps in the task? So to do this, we came up with 6 downstream tasks to evaluate our network. So the first is detecting the mistake steps. So we took an input video and we randomly swapped out one of the steps in the video with an incorrect step and introduced mistakes in the video. Then we fine-tuned these pre-trained representations to try and predict which step was incorrect. So this is in this task, we were detecting like which step is incorrect. In the next one, we're trying to detect if it can still find out if there are some videos where the ordering of steps is incorrect. So we take the input video and we randomly swap some steps. And so the goal of the network is to decide if the input video is in the right order or incorrect order. So that's mistake ordering detection. Then we're trying to detect the activity which is being performed in the task. So given the video, we're trying to predict the label. In the forecasting challenges, in short-term forecasting, you have about 5 steps which are provided as input to the network, and it learns to predict the very next step. In long-term forecasting, you take 1 step and you predict the next 5 steps and such. And in step classification, just assigning a label to the step. So what we saw is that our method was able to outperform like models which didn't use masking or which didn't look at other steps and achieve like improvements on all of these 6 benchmarks. So here's a qualitative result on which it performs well. So the task is cooking rice. And so one of the steps has been swapped out with like an incorrect step from another video of like making soybeans. And so the network is able to detect like the incorrect step correctly and also figure out which step should be present in place of the incorrect step. So yeah, some takeaways. We trained a video transformer model. We're masking out steps. And the learned step representations were able to capture task structure, which was missing in all of the prior works. And we can use this now to detect like mistakes in new user videos. However, there was still an issue with this. The main problem was using WikiHow, and the weak supervision from WikiHow is sometimes noisy. So as I mentioned earlier, we use the step labels for a particular task from WikiHow, but this is a generic set of step labels, and they might not always pertain to the video that you're looking at. So this particular video might have like new steps which are not present in WikiHow, or might like skip some steps which are present in WikiHow and so on. And so we try to see if we can fix this. So currently we're exploring this method where we're trying to use a large language model to obtain the step labels automatically from the transcript of the video. So no need for like any external supervision. So given a video, most of these instructional videos come with a transcript. Say like use your hands to form a mixture and such. And so now the goal is to try and see if we can prompt a language model to come up with the steps automatically from this transcript. So we fed it with this prompt, given this transcript from an instructional video, the steps in the video are. And turns out it's really good at doing this. So you can get the exact set of steps by just looking at the subtitles. And these are oftentimes very precise to the point where it will tell you how many grams of salt to add and such. And so we can get like very specific steps for any given video and don't have to rely on like generic recipe from WikiHow. Next, what we did was take these steps and localize them back in the transcript. So this gives you paired data between like the video and the steps because the transcript usually comes with timestamp annotations. So now if we repeat this across multiple videos, and we can then consolidate all of these steps, and we get a single recipe, which is now pertaining to all the videos in this task. So using this, we can now like create summaries. So we can essentially pick out parts of that video which only correspond to these steps. And if you stitch them together, that's going to give you a nice video summary. We can also train, like do this for all of how to 100M and train a video model, which would give you learned representations for each of these steps. And this way we can like extract step labels for all of how to 100M, which would otherwise require a lot of manual annotation.
Very quick question. Can I stop you? A lot of the times I've noticed that the ASR transcripts are just really low quality, like gibberish. On
Yeah.
out 100 million. Did you run ASR again, or maybe the GPT can somehow make sense out of it, or?
Yeah, that's a good
Or does it have
question.
Signal. I don't know.
Yeah, I guess like one thing is, even if we get these steps, sometimes they are noisy. There's no like way to actually evaluate them. So what we did evaluation was on the coin data set. So the coin comes with like subtitles and also contains steps. I think the subtitles we assume are just as noisy as how to 100M because they're like subtitles from the same ASR method. And so, yeah, I guess the words like the temporal alignment network work, which kind of like cleaned up the how to 100M subtitles. And so we're trying to follow a similar procedure to clean up the ASR before actually using it to extract steps. Yeah. But it works pretty well so far. And we saw like some of the results. Yeah, we've actually tried this on maybe 2 to 3 different tasks where we picked out about 30 or so videos and try to obtain steps from them and then localize the steps back in the original video by using dynamic time warping. And we noticed that like you can get some sort of structure across multiple videos too. So here I'm just showing one video. So this is just a video on how to like make burger. And essentially our method was able to take that original video and sort of extract the steps. And then when we localize the steps back in the subtitles, we can extract the video clips corresponding to those steps. And so that's what I'm showing here. It divides the long video into like 8 short clips. And we've performed this across many different videos on making burgers and how to make coffee and such. And we noticed that it can extract similarly like 8 steps from all of these videos. And so you can get this sort of consolidated structure across different tasks. And now our goal is to try and see if we can train a network to predict these steps by looking at the visuals only. So our method still relies on using the subtitles, but we would essentially want something which doesn't use any subtitles at inference time. So if a new user is performing this task and they say like make a mistake in one of the steps, we should be able to detect it without any sort of subtitles. And so that's where we're at right now, trying to train a video model which can predict these steps automatically and then have then evaluate it on like our own demo. So yeah. Which brings me to the last work on learning steps from multiple modalities. So as I was saying, we were trying to like use large language models to learn steps from videos. And here in this work, we're trying to actually learn steps, but to do a different task, just visual question answering. And yeah, I'll talk a bit more about this. So for those unfamiliar, VQA is just answering a question about an image. And this is one of the state-of-the-art models on visual question answering. So BLIP2 VQA, which takes this image and we ask it the question, what color is the horse? So BLIP2 is able to correctly answer it as black. So now if you ask it a slightly more difficult question, is the carriage to the right of the horse? It's going to say yes incorrectly. And the error in this method cannot be explained. So what if you give it a bunch of images? So like 5 images and you ask it a slightly more complex question. Are there the same number of images that have cake on a white plate as there are images that have a lemon on a white plate? Now this question requires like multi-hop reasoning. So you're gonna have to first detect the cake, images which contain a cake, check if that's on a white plate, and then count the number and do the same for the lemon. When you do this, it turns out the answer is yes. There's one image which contains a cake on a white plate and one image which contains a lemon on a white plate. And of course, BLIP2 gets it wrong. And again, there's like no way to explain why this is incorrect. So most of these like state-of-the-art VQA models are still missing one main thing, which is like interpretability. We cannot know when they're right or why they're right. And similarly, when they're wrong, there's no way to explain it. Also answering complex multi-hop reasoning questions, which require you to like break down the question, is still like an open problem. So that's what we try to do in this work. So first, we try to see how humans would answer these questions. So given a question and this particular image, so on which side of the image is the can, our way of answering this would be to break the question down into steps. So first we would like maybe locate the can in the image, and then find out where it is relative to the center. And then you can say that, okay, it's on the left side of the image. So how do we break a question down to steps though? And as we saw earlier, it's large language models are great at figuring out steps and structure from like unstructured data. And so we can use an LLM to break that question down into steps. So here we went a step further. We defined all of these visual primitives. So our main experiments use like 3 main primitives. Okay, yeah. So for this particular image, we try to like generate Python code given this question. So on which side of the image is the can? We're going to define each of these visual primitives, which allow you to get position of a particular object in the image, query the image for a question, and then find matching images. So given a sequence of images, you can find the image which matches a description the best. So now given these 3 visual primitives, we try to extract code from this question. So this is what it would look like. So given the question, first you want to try and use this get position primitive to get the position of the can. Now that you have the position of the can and you know the dimensions of the image, you want to try and see if this is to the left or right of the center. And so it generates a code which can exactly arrive at the answer in a systematic way. And so if your method outputs something incorrect, there's also easier way to decipher now why it was incorrect. Whereas in like the previous blip 2 example, there's no way to figure out why. So this is a pipeline of our method. So going back to the image of the horse, and the question is the carriage to the right of the horse. We few shot prompt the codex model with about 12 in context examples of such code snippets. So we just give it, image 1 on which side of the picture is the rug, and the code which is handwritten by us to solve this using the primitives that we defined. So get position, query, and find matching images. So with just these 12 examples, it can now come up with the code for this new question. So this new question is first, it's going to detect if there's a horse in the image. So if there is a horse, then the goal is to obtain the position of the carriage and the position of the horse, and then check their relative positions. So you use the get position primitive to get the position of the image, the carriage and the horse, and compare them to answer yes or no. So once this code is generated, we can also run this Python code because we have predefined these visual primitives. So the query module uses like a pre-trained network, which looks at the image and the question and generates a bunch of captions which are referencing this question. So the captions are now going to talk about this particular image, but also they're fed in this query. So they talk about like parts of the image which are relevant to the query. From these captions, we can then use another LLM, which will look at the query and the captions and come up with the answer. So the query only works on simple questions. So we always break the question down into like something simple, like I said, a horse and such, and feed these to the query. So this gives us yes for is there a horse in the image, and since it returns yes, the network also runs the two next primitives, which is get position of the carriage and get position of the horse. So for this, the underlying network is just a grad class activation map, which gives you a position of the carriage and the position of the horse, and then you compare the relative positions and return no. So this way you can go from the question to the answer in a very systematic way. And it's also interpretable. You can figure out if there was an error in each of these stages, and if so, why. So these are some of the results. We mainly evaluated our method on the data sets which require spatial temporal reasoning or like multi-hop reasoning. So 2 such visual question answering data sets are GQA and cover. So on code VQA, which is our method, outperforms the prior work, which is PNP VQA, on both of these data sets. So PNP VQA is trained in both like a 0-shot and a few shot setting. In the few shot setting, we ensured that we're using the same number of examples. Here in our work, we saw that adding more few shot examples is helpful up to the limit of like 12. And 12 in context examples, which were seen by our network, were like handwritten by us. So we handwrote 50 examples, and then we selected 12 of those by using an embedding matching technique. So you look at the question and match that to like the 50 handwritten examples and pick the ones which are most relevant to this question. And this is a qualitative result. So here, this is the cover data set where the network is fed multiple images. So it sees 2 images of the trains, and the question is it true that the train, which is right next to the platform, and the train that is near the snow are the same color? So essentially, it's trying to see if both the trains are of the same color, and the answer is no. This is the baseline method, which goes from the image to the captions, and then generates an answer. So as you can see here, it actually gets the colors correct in the caption. So it detects yellow and red correctly, but it still answers incorrectly when it has to like parse this information in the caption. So here's what our method does. It takes the images and then calls this find matching image primitive that I talked about earlier. It takes the images and tries to find the train which is next to a platform, and then tries to find the train near the snow. So using this, it can now get the color of each of these trains and then check if they're correct and if they're the same. And then it returns no correctly. This was the example that I showed earlier, where we looked at 5 different images and we asked Blip2 to detect which of these images, if there was the same number of images. And yeah, so like using our method now, we can see that first it breaks the question down into, is there a cake in the image? And if there's a cake, is the cake present on a white plate? And same for like, if there's a lemon, is the lemon present on a white plate? And it counts each of these occurrences and then checks if each of them are the same and answers yes or no based on this. So yeah, the main takeaways from this were that we have this modular approach for visual question answering, which uses few-shot code generation and all of these pre-trained visual modules. We noticed that program synthesis improves few-shot visual reasoning. And so if you were to do visual question answering without code generation, there's no way to interpret any of the mistakes. We also saw that it's easy to add new modules. So here we only tested it out with the 3 main modules that I mentioned: get, position, query, and find matching images. But you can add other modules like detecting objects, knowledge queries, which we've also tested out, and potentially this could work better in some settings. Also, selecting the relevant in-context examples matters a lot. So if we use the embedding matching technique to figure out which 12 examples to work with, and this provided like a performance boost. So what examples are fed to the codex model matters when it comes to answering the question. And in general, like having more inputs and more prompts led to like better improvement for the program synthesis. And so these were some of the takeaways from this work. Probably going to pause a bit for questions.
Well, we start with a round of applause. We have some time for questions, at least 2 minutes, probably even more.
Was there a way that you like confirmed the quality of the code that you generated before you ran it? Or like, yeah.
Yeah, so we could auto detect for any sort of errors in the code that it will generate, and like I guess most of the times we notice that the code is like runnable, like there are no errors in programs that it generates if the prompts that we gave it were correct. And so based on like the quality of the 50 handwritten examples, the code was like mostly correct. And other ways to check other than running it, I guess like, yeah, we just manually verified some of the examples. Beyond that, we didn't do anything automatic. Yeah.
So you would just run it, and if it doesn't run, then you just kind of repeat again and hope for the best.
Yeah, no, there's like if it doesn't run, then it defaults to like the baseline method, which is generating the queries. Yeah.
But you could just run it again, right? Presumably you get something a little different.
Yeah, I guess like that is true. You could like prompt it again. There is some, yeah, probably that it would generate something different, but most of the times it's something similar. Yeah.
In the IB sum work, like you collected this dataset for pseudo summarization, and like have you tried like if the model trained on this dataset can be like generalized to other unseen tasks, like if there are like a limited number of tasks in the dataset, right? So if like the model the model can generalize to unseen task and summarize the instruction.
I see. So like you mean if we evaluate it on something which is not summarization? Or
No, it's like it's still summarization. It's like just
oh,
task
unseen.
that's not in the
Okay.
dataset.
Yeah, we did. So yeah, we have a study where we show that like there's an overlap of just a few hundred videos or such where the task is the same. So it was trained on 12,000 videos, and in the 1,900 of them were all completely new tasks actually.
Okay.
So yeah, only 100 of them were tasks that the network had seen before. Because they're like WikiHow data set was collected by us, and it's completely different from the coin data set which we trained on. There are different distributions. Yeah. So it was able to generalize to unseen tasks. I think some of the things that like it picks up on are things like getting rid of promotional content that you see in the input videos. And this is sort of common across all of the tasks. And also just correlating like the subtitles with the visuals. This is something that the network learns to do by looking at the 12,000 videos. And so it doesn't matter if it's like a completely new task, it still performs pretty well on that. Yeah.
Seems that a lot of the issues like multi-hop reasoning that you tackled in code VQA are also present in the problems that you tried to solve with task former. A lot of the video data sets and those challenges are still present in videos. Are you looking at applications of code VQA to like the video domain as well? Seems like it'd be promising.
Yeah, that's a good question. So we are kind of trying that. There's like a video question answering data set, MSR VTT, where you essentially take all of the frames in the video, and you treat the video as basically a sequence of images. And since we use this on the cover data set, we can use it similarly on the MSR VTT data set and try to answer questions. So like generate code for answering questions. I guess like that's one thing that we've tried. Beyond that, for the other tasks, like using LLMs to generate steps from the instructional videos, it would be interesting. I don't know exactly how like generating code would be helpful there right now, but
Yeah, how far could you push that? I mean, can you think of a more unified use of code generation, not only for question answering as you have in the last part of the talk, but also in the earlier part, I mean, for activity mistake detection or even activity representation. Could you speculate on whether the code generation approach might be relevant there or how it might be relevant?
yeah. So I guess, one thing we're trying to do is look at like multiple videos and come up with one particular like sequence or structure that's common across all of them. And I think like what code generation could help with in this case is maybe trying to look at all of these like steps that you generate across videos, and you can perhaps come up with like code to verify if a sequence of steps is correct or incorrect. So you can perform the tasks in like multiple different ways, but it's hard to like define this ahead of time. And so maybe if a new user is performing a task, you want to construct like a recipe by using some sort of like video model, and then you could perhaps use like the code generation method to evaluate if their recipe is correct or incorrect. So I haven't quite thought about that yet, but yeah, something I could try.
Somebody else's thesis.
I was wondering if you had any thought of if this method could be extended to answer a question that cannot be like answered by code. Like, for example, is this image funny?
Yeah, that's a good question. I think
Wait, you're just trying VGG funny or something? It's all about the libraries you link in, right?
Yeah, that is true actually. So you can like link any module, like you can even link a knowledge module where it's just you're asking the LLM just the question and doesn't, when you can look at an image and maybe the question is who won the last World Cup, football World Cup or something. And so, yeah, it could like be a question for which you don't have to look at the image. And so, yeah, if you ask a question, I guess, is this image funny? You could perhaps like plug in another module, which is like trained to detect if images are funny and then have the code call that module. Yeah, potentially. Yeah. So I guess it's a way to like sort of stitch together multiple different modules and you can pre-train any module.
I wonder, so, you know, a lot of visual question answering stuff happening, but one could also think about flipping it around. And I guess it would still be visual question answering, but the idea would be that you would ask questions visually about something that you have read. So instead of seeing a video and then asking in text, you read a passage and then the text, the evaluation is like some cartoon that says, okay, is this image or this image? Have people been doing this?
That's a good question. I don't know, actually. That's very interesting.
Because that would be a way to kind of to evaluate grounding in these, you know, LLM models.
I see, but you would be using the LLM to sort of parse the input text.
That's right.
I see.
That's right.
Okay. And then
kind of compare somehow its mental model to, you know, is it A or is it B? Or maybe even a generative model, generative thing. I don't know. But the people haven't looked at that.
no, yeah, I don't think so. That's sort of like, yeah, opposite of like visual question answering.
Exactly.
An inverse problem. But yeah, I guess maybe even in that setting, I can see how this could be used. Because at the end of the day, whatever the text is saying, you could use some method which like constructs like a graph, like a scene graph or something, and then does the same for the image, essentially bringing them down to the same input.
I guess in the end, it should be like by direction.
Yeah.
One or the other, it doesn't matter. Yeah.
Yeah. I would assume it's kind of hard to construct such a data set though, with like questions being depicted as pictures or analogies. Yeah. That would be tricky. Is there any questions on Zoom? This is something.
How long is long? What's the longest video? And then what if you had to go another order of magnitude in length? What would you do?
Yeah, yeah, I guess I've thought about this. A lot of times, like when we work with the 2-hour-long videos, it essentially meant you're breaking the video down into smaller videos. So the max the network could see was at most like 20 minutes if you really downsampled the video and only pick like one frame every few minutes or something. And you could do that for like the egocentric videos, which were like of someone's day. And so for an hour, nothing's happening. So you can just essentially pick a frame. So yeah, I guess it depends on like what you want to do. So if it's just something like summarizing a video, I don't think like I think up to 8 hours is still fine. Essentially what you would do is try to find a way to like pick the events and then the events that you want to focus on. And so this can be done like sequentially and you don't have to look at the entire video at once. But if it's something like very specific questions, then you need a way to like look at the video in like a hierarchical manner. So extract like the high level information represented as like something more than scenes, and then figure out which of the scenes that you need to dive into and sort of break the video down into smaller videos. And I think this is what we sort of try to do with the task structure work, where we have the hierarchical transformer looking at the smaller video segments and then trying to parse them together jointly to understand step information. But yeah, maybe something more explicit would be defined what's the sequence of steps in the video.
Any last question? If not, let's thank Medhini again.
Well, thanks. I guess there was just some other stuff that I wanted to share.
You have more slides?
Oh no, it's just like what I'm gonna do next and wanted to
Oh, wait.
share. No,
Sorry
no.
about some, but it felt like you had ended your talk.
Yeah, it is. It's just acknowledgements.
Okay, hopefully these are cartoons.
Oh yeah, this is just cartoons, but I guess as most of y'all know, I'll be headed to Google next, and I'm going to continue working on summarization actually, but more focused on YouTube now. So sort of deploying maybe some of these models and trying to see how they work in the real world. So yeah, excited to like maybe collect real world data for this problem. So that would be cool. Yeah, and I guess this is, maybe I can go in acknowledgements. So I wanted to start by thanking, oops, that should not have popped up. Thanking Trevor, my advisor. Yeah, you've given me so much freedom and flexibility over the last 4 years. I've always appreciated that. Thanks for your guidance. And I think I grew a lot as a researcher, learned a lot about managing projects, managing people, and doing good research. So thank you so much. Of course, the rest of my committee, Cordelia, who's been my mentor through internships, and Alyosha, also here at Berkeley, mentoring me and guiding me from the beginning. Thank you. And Jitendra as well. I'd also like to mention my previous advisors from UIUC. The main reason I got into research and was excited is because of them, Alex and Lana. Yeah, and I guess I came in as an undergrad not knowing what to do, and they sort of took me under their wing quite literally and taught me the very basics and wrote my first few papers with them. And yeah, I appreciate all that I've learned and something that I will take on with me as a researcher. I'd also like to thank the rest of my collaborators. Yeah, Anya, who just left for Germany, but she's worked with me on so many projects and I've learned a lot from collaborating with Anya, and especially a lot of writing skills I have now is thanks to Anya editing my overleaf last minute. And Arsha, Andrew, Mickey, Chen, Sanjay and Andy, and also undergrads who are working with me or have worked with me in the past, Emmy, Chui, and Jacob. Thanks a lot for all your help. Also wanted to make a shout out to Berkeley Climate Initiative, Colorado and Ritwik. We started this together about like 2 years ago now, where we were just reading papers about at the intersection of AI and climate, and this turned into something big. And so if you're interested in learning more about this, do attend our bi-weekly meetings, and also just reach out to Ritwik, who now leads this group. But yeah, we had some cool projects. I got to work on like using vision for detecting elephants in Africa and collaborated with an NGO there. So it's cool stuff that you can do on the side. And I really appreciated being able to do that during my PhD. And also, I guess I want to start with thanking my family. My mom, okay, yeah, my mom who's on Zoom, hello, and she's been like the biggest support my whole life. She's also the main reason I take a lot of, I guess, I've been taking risks and trying to push my boundaries and goals. Yeah, my mom's the most like badass woman I know, and she's taken such big risks in life that she always continues to motivate me, and she's been a source of strength throughout and supporting me and encouraging me always. So thank you. And my dad, I guess my dad taught me a lot of the values that I follow still today, and yeah, like was a big part of my childhood. Yeah, and I'm forever grateful for everything that I've learned. My granddad, he's probably the only engineer in our family, the first one at least, and I was always interested about like AI even 10 years ago and asked me questions about it, and one of the main reasons I got into engineering was because of my granddad. And this is my family in Florida, my aunt and uncle, Giri and Kalai. They're also professors, and I learned a lot about research from them first and have worked with them too. So it's been great to have them around and constantly guide me. And my cousins up in Seattle, and yeah, I'm thankful for all their support over the years. Of course, I have to mention my dog, who's not around anymore, but was like so. Yeah, it was a big part of my life. I also want to thank all of my friends. Yeah, thanks so much. There's a lot of them that I try to fit on the next set of decks, but yeah, I think like the PhD is a tough journey, and so having a support system was extremely helpful, and that's the only thing that got me through this. Friends who were like actually present and to like talk to and to go to. So yeah, I don't know what I would do without like friends who made me laugh very often, pose in front of toy stores when I asked them to, and yeah, friends who were just ready like down to be clowny with me, and friends who pretended to be Egyptian. yeah, have more of these embarrassing photos. But yeah, I guess post-COVID PhD was great and a lot of good experiences to remember. Yeah, a lot of my friends were on Zoom. Yeah, I guess I went backpacking a lot and explored a lot of California during my PhD. Thanks to them, they were always down for a backpacking trip in Yosemite anytime I asked. Would also plan it. And of course, my biking crew. Couldn't fit everyone here, but yeah, thanks. And yeah, friends who would climb up and down Grand Canyon with me if I wanted to. And yeah, this is back in first year. I guess this group kind of died down with COVID, as we say always. Yeah, we thought we were going to build a snowman every year. It did not happen. Yeah, it was a great start. And yeah, I guess despite COVID, it was kind of nice to have a lot of these enjoyable experiences. And yeah, I'd like to thank friends who are not here, but remote and have been extremely supportive. Not just in the PhD, I guess some of them since high school and even before, it sort of like motivated my journey so far. So thanks so much. And yeah, some of them are on Zoom, so hello. So yeah, and friends who are always ready to travel with me and do fun stuff. So thanks for all of that. I really appreciate it. And of course, all of the lab camping trips. Yeah, I'm glad that I still have permission to attend those, but I shall come back with funding, as you mentioned. But yeah, I'm gonna miss the lab camping trips for sure, and all of the hikes. That's been extremely enjoyable. Thank you. That was it.